Artificial intelligence is an integral part of today's society and our companies' users of state-of-the-art mobile devices daily. In its form of machine learning, AI has achieved tremendous success in image and video recognition or natural language processing, to name a few examples. Apple's Siri, designed as the first personal assistant for a mobile device, is already over 13 years old. Based on its success in these areas, the wireless industry started to explore how AI and ML can be used to optimize wireless communication, starting with network management and orchestration, but then also looking into the aspects of signal processing tasks for 5G Advanced and a future 6G air interface. Over the past months, we started here to explore the fundamental concepts of AI ML through webinars or as part of our Think 6 video series. And today I would like to welcome you to our Rohde Schwarz Tech Talk, where we continue to investigate these fascinating concepts. And of course, we can only do this with support from our technical experts. So I would like to welcome Andreas Oeldemann to this talk. Welcome, Andreas. Can you introduce yourself and your role here at Rohde Schwarz?
Sure. Well, first of all, thanks for having me here. I'm also Andreas, so we try to make it simple for everybody. Andreas Oeldemann. I'm part of corporate R&D here at RNS, and I'm program manager for AI and wireless communication. So with a team of experts, we are working in the intersection of wireless communication on the one side, but then also machine learning on the other. And our major focus, I would say, is 6G. So a lot of industry key players believe that machine learning will be a major part of 6G, not only in the network orchestration, as you mentioned already, but also in the air interface, in the physical layer. So our role is here to investigate how does this impact test and measurement, and how can we best support our customers in the future in testing these AI-enhanced devices under test and ensure interoperability in the end.
Okay. So AI native in 6G will be definitely a topic, so I want to talk about this a little bit more a little later. But first I would like to start with a question and getting your take on, does that mean now we need machine learning engineers that understand wireless, or do we need the wireless experts become masters of machine learning? What would be your take from your experience?
I think the simple answer is we need both. There has been decades of research in the wireless context, and we can't just throw this all away and just apply machine learning all of a sudden. So instead, my opinion is that we need to take all these wireless expertise that has been built up over the last decades and build with machine learning on top. So you definitely need experts that master both fields.
Okay. And then as probably everybody knows by now, because this is such a buzzword, such a topic in every area, training, right? Training is an integral part of machine learning and such. So what does that mean in the context of wireless communication, right? So can you help us to understand that a little bit better?
Yeah. So let's maybe take a step back and look at what machine learning actually is. When we talk about machine learning, what we mean is, instead of programming a machine to do a certain job, we let it learn from data. So data is really key here. Training is an important step in this entire process. We have a certain data set, we have a certain expected result. So we're talking about supervised learning typically, where our data is labeled, and we want to train, for example, a neural network that allows us to do a mapping from the input data to the output data with a minimum error, I would say. And training is the process of exactly achieving this. In the wireless domain, let's maybe look at an example. A lot of researchers are, for example, looking at channel estimation. Channel estimation is certainly a topic that is not new. Lots of research in the last few decades, but still, there are some channel models that we're dealing with today that we can test and design this channel estimation with. But the question is, how does that really perform when it's deployed in the wild, in the field? Mm-hmm. And researchers are investigating here, if we learn such a channel estimation from data that ideally has been collected in the field, can we perform better? That's just one example.
Okay. So we mentioned the data as a critical part in the training process. I think that totally makes sense to everybody. So we already touched a little bit on that. So where is that data originating from? Where it's coming from? How we get that data, right? Because no data, we can't train these models, right? So what is key here?
Absolutely right. Data is key. So in the wireless domain, I would say, especially when you look at standardization, we talk about this in a bit, a lot of companies, a lot of researchers are working on artificially created data in simulations, just to get a basic understanding if machine learning can actually do what our conventionally designed algorithms can do. But then when we're thinking more about a deployment actually in the field, then it's really key that we train this on real world data eventually to maximize performance. When it comes to wireless communication, again, the wireless channel, that's typically the big unknown. We want to train models that can cope well with the previously unseen wireless channel. So wireless channel measurements in our domain are quite important to train these models.
Okay, very good. So we talked a little bit about the training, the data. How does the training process look like, right? Can you describe that to our audience a little bit?
Yeah, without going too much into the details, because this is quite a complex topic, let's maybe look at supervised learning a bit. So you have a certain data set, that's the input to your neural network, for example, and you have an expected output of the neural network. That's typically your label. Now what you do is you feed this data set into your neural network and look at what's actually the output. We call this process the forward propagation. Now, when you start this, you have an untrained neural network. So basically all the weights and biases of your neural network, they are not initialized correctly. They may be initialized randomly or with some other approach. So the output that you are seeing at the neural network in the beginning does not really match your expectation. The neural network does not perform well. Mm-hmm. So how do you get the network to actually perform the job of mapping a certain input to the expected output? This is the process that we call training. Now, to quantify how far is the output away from what we are expecting, we are typically using loss functions. That gives you a metric to determine again how close are we to getting to our optimization goal. We want to minimize this loss function, so small loss is good.
Of course.
To do this, we do the training, and here are two steps involved. The one thing is what we call backpropagation. So basically, we are calculating the gradients of all the parameters of our neural network, so weights and biases, in respect to the loss function that we're seeing. And what this allows us to do really to determine the direction in which we need to change the weights and biases such that our loss functions will get minimized, will get smaller. These gradients that we're calculating in the backpropagation, so in the backpropagation, we're starting from the loss function and then backpropagating through our neural network from the end to the beginning. We're calculating all these gradients, and these are the inputs then to our optimizer that actually determines how the gradients, how the weights and parameters are changed.
Okay, very interesting. So we talked about the neural networks. So I assume there are different architectures that are being used for different tasks. Is there anything that's dominant while we're talking about machine learning in the context of wireless communication?
I really guess it depends on the problem that you're really trying to tackle. I think the easiest neural network structure is what we call a dense structure or fully connected structure. So you have your set of neurons, and all neurons in one layer are connected to all neurons of the next or the previous layer. That's a very simple structure. From image processing, we are used to deploying CNNs, or convolutional neural networks. Mm-hmm. These tend to work very well for image processing, video processing, where you have a high correlation between neighboring pixels. In wireless communication, again, looking at OFDM resource grids, for example, this is also a property that you can exploit, and CNNs work quite well there as well. Then if you want to predict time series, for example, you have recurrent neural networks, LSTMs, you have transformers these days a lot, influenced by also the huge success of large language models. So it really depends on the problem that you're trying to tackle.
So I guess, like you mentioned, recurrent neural networks. I mean, they would look into the time series, so basically model the memory effects, right? If we have problems like that, for instance, the linearization of our front end. So I guess that would be an area where you would apply those kind of things. So if you start getting more familiar with this topic, right? If you do your literature study, like many of our customers would do, once they're approaching 6G, as an example. I would assume that they run into the already mentioned CNNs, but then they also run into autoencoders, right? So can you describe to us what is an autoencoder?
And an autoencoder is quite a special structure. Like the name suggests, auto, you want the input of the neural network to actually match the output of the neural network as closely as possible. Now, the constraint that we typically have is that somewhere in the middle of this one neural network, we have a bottleneck. So we basically want to reduce the size of the information, want to compress the information. This is something that allows us then to do an efficient communication, for example, over the wireless channel. You can think you have one neural network, so this is the first part of your autoencoder that does compression. Then you have this bottleneck, which we call latent space in the middle. This is actually what's being transferred over the air. And then you have this decoder neural network on the other side that tries to reconstruct these information as accurately as possible.
Okay. So I'm super happy that you mentioned already two other terms that people will run into while they start studying machine learning, right? Not just in the context of wireless communication, but generally speaking, latent space, ground truth is another one, right? Can you help us to understand the meaning of those two in that context?
Yeah, so latent space, we addressed a bit already. So latent space in the autoencoder context is this space, this bottleneck in the middle of the autoencoder, basically the compressed representation of your information. When we're talking about ground truth, in autoencoder term, again, the ground truth, you provide a certain input to the autoencoder, that's your ground truth, and you want the autoencoder to reconstruct your ground truth as accurately as possible.
Okay.
Ground truth in general, in terms of neural networks, you could also say your labels are your ground truth. So your expected outcome of the neural network.
Okay. So I want the audience to hold that thought on the autoencoder. We will come back to that here in the context of wireless communication. As Andreas and I mentioned already in the beginning, this is currently explored. It is explored in 5G Advanced with 3GPP releases 18 and 19. For the very first time, from an air interface perspective. It's not new to 3GPP. We had also in release 15 already the network data analytics function to help cope with the data analytics in the core network, to help with network management, orchestration tasks, network functions contributed that data to those functions. So it's not new in 3GPP, but it's new on the air interface side. And that's, I think, also one of the very challenging and interesting areas while we moving towards 6G. So Andreas, as you're working on this, how is 5G Advanced looking into this and what areas they're focusing on? Can you summarize that for us?
Yeah, sure. To give some context, we're in release 19 right now, and the study on the AI native air interface actually started in release 18. The study was started with 3 use cases, and we can briefly go over them real quick.
Yeah, please.
So the first one is AI/ML enhanced positioning. So think about indoor factory environments, for example. This is something that's being studied in 3GPP, where you have heavy non-line of sight conditions, and you want to determine the position of a certain UE, a robot maybe. Doing something like that with conventional algorithms is really challenging and not that accurate. So what 3GPP is studying, can we benefit from AI/ML here? To use wireless channel measurements and then with AI/ML predict the location of a certain mobile device. This has been quite successful in the study item in release 18 and actually made it to a work item in release 19. So this is something that is actively being standardized.
Yeah. So for the audience, just like work item means it becomes actually really part of the standards. So it will be implementable. And then, of course, it will be also becoming testable, so to speak. That means the 3GPP will take care of test cases that are designed around this feature or this functionality. So please continue on the other aspects.
Sure. So the second one is AI/ML enhanced beam management, and quite similar, also started in release 18, also a work item in release 19. So as you know, at high frequencies, FR2, we're relying heavily on beamforming these days. And typically a UE needs to perform multiple measurements to actually determine what the best beam is that it sees, which beam to use. Now these measurements, they consume power, they cause a certain overhead. And what 3GPP is exploring, can we use AI, ML here to actually do a prediction what the best beam is? Yeah. So prediction here means, on the one hand, a temporal prediction, so best beam in the future. So we just do less measurements over time. The second one is also prediction in spatial direction. So can we just measure a subset of the beams and then predict based on the small set of measurements which is actually the best beam?
Okay. So that's 2 out of 3. What's the third one?
CSI feedback enhancements. Also release 18, made it into release 19, but only parts of it. Because CSI feedback compression is one topic. Yeah? So how can you compress channel state information that are frequently sent back from the UE back to the base station and cause a certain overhead? This is where the autoencoder comes into play, and I think we'll discuss this a bit more. But we also are looking at CSI prediction. Yeah, so how can we predict channel state information in the future? And that actually made it into a work item with release 19.
Okay. So let's stick to the CSI feedback enhancement pilot use case that you mentioned, right? So obviously it's still, part of it is still a study item. I think the major part of it, right? The compression part. I think a lot of companies argued we still need to study this more. So it seems to be challenging. So where are the challenges in this part of that pilot use case, the compression part?
Sure. Let's get back to the autoencoder again. Yeah, we briefly talked about this already. We have these autoencoder that can be decomposed in 2 models, an encoder model and a decoder neural network. So what happens with CSI feedback compression is that you have UEs that execute the encoder portion of the neural network. Yeah? You compress the information using this encoder, transfer them over the uplink back to the base station, and the base station has the decoder neural network and decompresses these information. So we have a so-called 2-sided model. Now the challenge here is that these 2 models, they need to be interoperable. They need to be trained in such a way that they're working with each other. And while there are many technical solutions to do that, it proves to be challenging in 3GPP because there are not only technical constraints, as always, we have political constraints. So companies are not really willing to open up their models, disclose their IP, and that makes things tough. There are, again, technical solutions for all these issues, but it just takes 3GPP a bit longer to figure all this out and to standardize this eventually.
Okay. So as there are many, many companies trying to collaborate, work together in 3GPP, you already mentioned the different aspects of it and how people are looking into that. I would assume that we need to narrow it in, right? We need to agree on a certain structure, on a certain model, so to overcome all these hurdles that are there. So what's the status right there within the standardization right now?
Yeah, so interoperability is key. The models need to work together. And we need to ensure that this interoperability can actually be verified, can be tested. And this is where our expertise, where Rohde Schwarz comes in. Yeah. So our company, our team, we're contributing actively to RAN 4. So this is the testing group within 3GPP, and are contributing how these models can be verified in the end. Yeah. So currently 3GPP is discussing several different, they call it reference decoder models that could actually be standardized in the future. And that would then be executed by the test and measurement equipment and allow our customers, for example, to test their UE implementations against a certain reference implementation, basically.
Okay. So basically we would verify or prove, validate the fundamental procedures, how different models, maybe for different environments, I would assume, are exchanged. What is the procedure in 3GPP so that a mobile that is powered by chipset A works with infrastructure, vendor equipment B, and so forth, right? So I would assume that is just to lay the foundation. But then, of course, the companies see additional benefits in designing their own models that they, of course, don't disclose to 3GPP then, but maybe to their customers, the service providers that then implement 5G advanced functionality. Is that the case that we see compared to today's methodologies, how we're doing channel state feedback, performance gains? Because otherwise, why we do it, right? So what is the benefit actually of approaching this through machine learning?
Yeah, so this is my personal opinion, but I have the impression that 3GPP is doing, let's say, baby steps to learn how to standardize these procedures, yeah? Especially two-sided models. Like I mentioned already, it's complex to do. Yeah? And to be honest, the benefits of CSI feedback compression are conversely argued within 3GPP. Yeah? The benefits are not that big, and it certainly introduces quite a bit of complexity in terms of standardization. Yeah? So for me, again, this is a very simple use case that we're looking at, and I have the impression that 3GPP is just preparing, for what's coming in 6G and learning how to standardize procedures around training and testing and execution of two-sided models.
Yeah, that's a very good point. I think with 5G and 5G Advanced, we already set the framework that we have to operate in, right? So as we all know, it's easier to start from scratch, right, and have all the degrees of freedom to do stuff instead of bringing it into an existing mechanism, right? So I think that might be one of the challenges associated to this. When we're talking about the channel state information enhancement here, or the feedback enhancement, I ran into the terms implicit and explicit, right? And I think people sometimes, mix them up while they're talking about the gains, the performance gains that are being seen. So can you shed some light on this, and enlighten us a little bit what implicit is, what is this related to, what explicit means, and what the whole context here is in terms of channel state information?
Yeah, so these are terms that you quite often find in literature. Yeah? So implicit channel information basically means instead of transferring the entire estimated channel matrix from the UE back to the base station, you just transfer back the eigenvectors, the precoders, basically. This is very close to how 3GPP codebook-based transfer of the CSI is standardized today. What we see in research quite a bit is the explicit approach. This is where you actually transfer the entire channel matrix back to the base station. And that just gives you a bit more information on the base station side that the base station can work with. But exactly like you mentioned, this explicit feedback is quite different to what we have standardized today in 3GPP. So we need this fresh start, let's say, with 6G to explore these concepts further.
So if I understand it correctly, that would mean we built the expertise with 5G Advanced by reducing the complexity, looking at the implicit feedback, compare that to the existing methods that we have. We don't see that huge quantum leap forward, right? The huge gains, we see gains, but not as significant as some literature may suggest. That then refers to explicit feedback. And the explicit feedback part is something that, while we master the foundation in 5G Advanced, is something we could do then in 6G. Would that be a fair summary of the state?
I think it all takes time, right? And there are many open questions that need to be answered. And we're all excited to see what's really coming to 6G then.
Yeah, okay. With that, I would like to thank Andreas for the first insights, looking into 5G Advanced, how machine learning is applied, which pilot use cases are being investigated by the standardization body, and specifically talking about one of the challenging items, as we heard, the two-sided models tackling CSI feedback enhancement. Thank you, Andreas, again, and I hope to see you soon in a future Tech Talk, where we then explore additional areas, specifically around 6G, talking about AI native air interface for 6G, neural receivers, and all that good stuff. So stay with us and join us in one of the next Tech Talks, brought to you by Rohde Schwarz.